So section 6.6 is a section on solving equations. That's problems that have equal signs. When we have problems with equal signs, we can get numerical answers and we can check our answers. The first 12 problems, I'm going to solve them all more or less the same way. I'm going to rewrite the problem so that both sides have a base and an exponent, and the base needs to be the same. In problem 2, the left-hand side has a base of 3 and an exponent of x. What I need to do is rewrite the right-hand side so it has a base of 3 and some exponent that's a number. If I can do that, if I can write both sides of an equation with the same base and a different exponent, then I can solve the problem by just scratching out the bases and setting the exponents equal to each other. So for all the problems 1 through 12, I'm going to do prime factor trees. Mostly I'm going to do the prime factor trees in my head because I know these in my head, but I'll show you 1 or 2 by hand. So for problem 2, I need to get a prime factor tree for 27. 27 is 9 times 3. I put a V under 27, wrote any two numbers that multiply to 27. The 3 is a prime number, so I'll circle it. 9 is composite or not prime, so I put a branch or a V under it. 9 is equal to 3 times 3. So the prime factoring for 27 is 3 times 3 times 3, which is 3 to the third power. Each of the problems between 1 through 12 is very carefully constructed so that it's possible, if you do 1 or 2 prime factor trees, to rewrite the problem so that each side can have the same base. And if I can get each side of an equation written with the same base, then I can solve the problem by canceling out the bases and setting the exponents equal to each other. When the exponent's just an x, I have my answer. I gotta imagine some of you already knew that 3 was the answer. If I want to, I can check every problem I do. How do I check? I take the number that I think is the answer, plug it in for the letter, and make sure I'm left with a true statement. So I don't know what calculator I've been using this for the videos this term, but I'm re-recording this video because I'm doing some problems differently, so I might have a different calculator right now, but I just did 3 up arrow 3 just to check. I have the answers written down for all of these, and maybe to save a minute I won't check every problem. That's all there is to do for 2. On the test, the problems might be slightly more complicated where you couldn't just look at them and know what the answer is. For instance, on problem 4, maybe you don't know that the answer to problem 4 is 2. So problem 4, just in case it's not showing up so well, almost looks a little blurry on my screen. The problem is 3 to the x plus 2 equal to 81. Each of the first 12 problems are designed so that if I do a prime factor tree for any non-prime number, that I can get both sides written with the same base. The base is going to be a small number, but it's not always going to be 3. So under 81, I wrote 9 times 9. Neither of the 9s were prime, so I put a branch under the first 9, or upside down V under the second 9. And I can see that my prime factoring for 81 has 4 3s in it, or it's 3 to the 4th power. So I can rewrite problem 4 as 3 to the x plus 2 equals 3 to the 4th. If it's possible to get both sides written with the same base, then you can drop the bases and equate the exponents. Now I have to do one step to isolate the x to get my answer. My answer for problem 4 is going to be x equal to 2. And if I want, I can check by changing that x to 2 to see if 3 to the 2 plus 2 power equals 81. I know it does. I'll do it on this calculator really quickly. 3 exponent. On this calculator, because it's a little bit older and it doesn't show the exponent, I have to use the parentheses for the exponent. If you have a slicker calculator where it shows the exponent, you go 3 exponent 2 plus 2, If your calculator shows the exponent, you don't need the parentheses. So depending on how new or old your calculator is, if you have one of the older TI calculators that doesn't doesn't show the exponent, if the exponent has adding or subtracting in it, you need to have it in the parentheses. On the newer 80 TI calculators, it will raise the number for you and you wouldn't need a parentheses. 5 and 6 are tricky. First of all, the left-hand side of 6 is the hard part. I'll do it on this calculator. I'll show you that what I'm going to do. What I'm going to do is I'm going to rewrite the left-hand side of 1/3 with a negative exponent, just in case it's not showing up so well. 1/3 is the left-hand side. The right-hand side is 27, which has a prime factoring of 3 cubed, which I did already. This 1/3 is really 1/3 to the first power, and that's actually equal 3 to the negative 1. So this left-hand side, I can rewrite it as 3 to the negative 1 to get it to have the base of 3 that I need. And I'll show you that 3 to the negative 1 is equal to 1/3. There you can see it. So if I have a base as a fraction, I need to change that fraction into a negative exponent. What I do is I just take whatever's in the denominator with its exponent made negative, and it no longer needs to be a fraction. Now, to clear the parentheses, I need to multiply the exponents. So this is going to give me 3 to the negative 1 times x equals 3 cubed. Now I have the bases on each side the same. Lots of 3's here, but they aren't always going to be 3's, but they're going to be small prime numbers more than likely. Drop the bases, set the exponents equal to each other. I'm going to solve by dividing. I'll just box it here. I'm about to have an answer. My answer is x equal to negative 3. If I wanted to check, it's a mess on this calculator. If I wanted to check, I'm going to take this x and make it negative 3 and make sure that I match up with my right side. So let me try to just do this real quickly. Parentheses 1 divided by 3, exponent, little up arrow, negative 3. And this gives me 27 equals 27, which is perfectly exactly what I need. So I checked perfectly. For problem 8, which is kind of tricky, I need to do a prime factoring for 243, which is 3 to the 5th. If I do 243 divided by 3, that tells me 243 is 81 times 3. 3 is prime. 81 I know is 9 times 9. Neither 9 is prime, so I branch both of them. And now for each 9, I make a 3 times 3. So the prime factoring for 243 has 5 3's in it, which is 3 to the 5th power. So initially, just in case this isn't showing up so well, the problem said 3 to the 5 minus x equals 243. I'm going to change this to 3 to the 5 minus x equals 3 to the 5th. Now I'm going to set the exponents equal to each other, and I'm going to emphasize that that x really has a 1 in front of it. It might help me do my algebra. So this is really 5 minus 1x. I don't normally write the coefficient of 1, but here it might be useful. I'm going to subtract 5 from both sides and get negative 1x equals to 0. I'm going to divide by negative 1. On the left-hand side, the two negatives cancel and I get an x. On the right-hand side, fractions with 0 in the numerator are equal to 0. To check, I need to change that x to 5, x to 0. So it's 3 to the 5 minus 0 power equal to 243. Well, this is just 3 to the 5th power is 243. And that's what I just figured out. But I can do this in my calculator. 3 to the 5th power is 243. So I get a perfect checking. up through problem 12, we'll be able to do perfect checking pretty easily, and it's not really 100% necessary to check. Let me autofocus this. I'm not really excited about how it's looking right now. I don't know if it's going to do any better since I already autofocused. For problem 10, which is 27 to the x equals 3, the 27 needs a prime factor tree, which means it's going to get an exponent, and it already has an exponent. It's appropriate when this happens, if you're going to do a prime factor tree for a number that already has an exponent, to put that number that needs a prime factor tree in a parentheses. 27 I've had a couple times, so I'm going to make it 3 cubed. And on the right-hand side, there's an implied exponent of 1. So I get 3 cubed to the x power equals 3 to the first. I need to multiply these exponents so I can clear the parentheses. This gives me 3 to the 3x equals 3 to the first. I cancel out the bases and set the exponents equal. Now I divide by 3, I divide by 3, and I get an answer of x equal to 1/3. If I want to check, I should go to that x, change it to 1/3, make sure it equals to 3. So 27 exponent, I need a parentheses because my calculator doesn't raise the exponent for me. And I did perfectly here. I get 3 equal to 3. Checking is completely optional. I have the answers already typed up so I don't make a mistake on the video and have to record it again. But it's never a bad idea to check. So 12, just in case it's not readable, is 49 to the x equals 7. Same style of problem. I need to do a prime factoring for 49. 49 is 7 times 7. So the prime factoring for 49 is 7 squared. The right-hand side, the 7 needs to have an exponent of 1. I need to multiply the exponents now to clear the parentheses on the left-hand side. Drop the bases of 7, set the exponents equal to each other, and divide by 2, divide by 2. And I get x equal to 1/2. That's the easy part of this section, but these problems were very carefully constructed so that it was possible to make the bases the same by just doing prime factor trees. Once we get beyond number 12, it's not going to be possible to use the strategy of writing prime factor trees, because the prime factor tree for 10 doesn't have only 2. So when I look at problem 14, 2 to the x equals 10, that's not good because the prime factoring for 10 has a 5 in it, and you can't just set the bases equal to each other unless it's possible, because the problem's set up to be solved that way. When it's impossible to write the right side with this as a power of the left side, you have to write the problem as a logarithm. And how do we write logarithms? I write the word log, so I'm going to solve this by introducing a logarithm. I'm going to write the word log, and this 2 is going to be subscripted. And I'm going to switch the x and the 10. So the 2 becomes subscripted, the 10 becomes the argument of the logarithm, and the x comes free. This is the answer. This would be kind of ugly to check. So I'm going to get a decimal approximation for this. On my slick TI calculator that broke, there's something called log base under the math feature. If you hit your math feature and like arrow, 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 and you see log base, then you've got a better calculator or a newer calculator than I do. So log base would allow me to do this, to get a decimal approximation. I would just hit the log base, and I could type log base 2 of 10, and around to 2 decimals, I'm going to say this answer is about 3.32. To get a decimal for checking on this big calculator, I would have to do log of the argument divided by log of the base. So this would be log of 10 divided by log of 2. So if you don't have the log base, that's how you get it. And the more decimals I include when I'm checking, the more accurate my answer is going to check. If you're checking a rounding, it's not going to check perfectly. So if I went to check this by changing the x to 3.32, well, what's supposed to happen is both sides of the equation should be the same number, so the left side should come out to 10. But if I do 2 exponent 3.32, I get 9.99 if I round. So it's not a perfect checking, but if I checked more decimals, if I did all this, if I did 2 exponent 3.32192.809, and then look how much better it checks. It's not going to check perfectly when you're checking a decimal approximation. You're getting rounded answers, but 9.99 is close enough to 10 that I believe my algebra is right. Each of the problems between 13 and 24, we're going to write the problem in its logarithmic form, and then maybe have some algebra to solve for x, or maybe just have an answer. 4 of the problems, 17, 18, 19, and 20, aren't perfectly set up to write it as a logarithm because there's a multiplication on the side with the exponent that we'll need to deal with. I don't put those on the test, but I sneak them in the homework. So 16 says e to the x equals 1.15. All the problems between 12 and 24 I'm going to write with a log. This is going to be the base, so I'm going to introduce a logarithm, and I'm going to switch. I'm going to create a logarithm. So I'm going to get the log base e of 1.15 equals x. This is a great answer, but not the best answer. Log base e and ln are the same. So if I did this on this calculator to get my decimal, log base e of 1.15, I get 0.13, whatever that is. On this clunky calculator, if I did ln of 1.15, I get exactly the same number. Those numbers are exact to however many decimals there are. Log base e is great for doing algebra, but it's not usually written in answers. If I see log base e, I probably should improve my answer by replacing that log base e with ln. ln is the same as log base e. This is a better answer. And regardless of if I had the log base or if I just had this calculator, which doesn't have log base, I can get a decimal answer. And 0.14 is rounded to 2 decimals, but 0.13976, maybe I'll check. I don't need a decimal answer, but for checking purposes, decimals are better. So let me see if e to the this, so for my checking, is e to carry a bunch of decimals, 0.13976, is that equal to 1.15? Probably, or close to it, won't be exact. How do I get e with an exponent? I hit the second button, followed by the ln key. You can see right above it, it's in blue, e with an x. Now I'm going to type my answer, 0.13976. The more decimals I carry, the more accurate this is going to be. So this tells me 1.14999 equals 1.15. I feel good about that. On a test, you don't need to give me a decimal answer. The answer with the logarithm or the natural log, depending on the kind of problem, is preferred. But if you give me a decimal answer, I'll live with it. 2 decimals is all I ask for. But if you check with 2 decimals, like if I check this second ln 0.14, it's not as nice of a checking. It's close enough for my purposes to believe that I'm right, but it's not as good of a checking as carrying 5 decimals or carrying 8 decimals. 17, 18, 19, and 20 are the 4 problems where the part with the exponent isn't isolated, and I need to get it isolated. So in problem 18, this 4 that precedes the exponential piece, the 3 to the x, is not conducive to turning it into a logarithm. So I need to isolate it. This is what I need. This is what my hints up here meant. For these 4 problems, there's going to be a number that's the exponent doesn't apply to, that's multiplied by the term that has the exponent. I'm going to divide by that number. Now I'm going to write it as a logarithm. The 3 is going to be my base, and I'm going to switch the x and the 6 and get log base 3 of 6 equals to x. This is my answer. I want to get a decimal equivalent for that. On this old calculator that doesn't have log base, which your calculator may have if you search for it, I get 1.63. And on this calculator that has log base, which is my favorite calculator, I get 1.63. Again, if you give me a decimal answer, 2 decimals is fine. I don't need a decimal answer, but if I was checking, maybe I'll check 4 decimals. I'm not being consistent because it doesn't matter. So I need to see if 4 times 3 to the 1.63, however many decimals I want to carry for accuracy, the more decimals you pick, the more accurate your checking is going to be. If it doesn't worry you that you're not super close, that maybe you're off by a tenth, then check just the 2 decimals. So on my old calculator, 4 parentheses, 3 up arrow, 1.6309, close my parentheses. I should be close to 24, and this again is good enough for me. That's close enough to 24. If I carried more decimals, I'd get closer to 24, but this checking certainly makes me feel that my answer is correct. (20) and 19 are the other 2 problems that aren't very good for solving using our strategy, because there's a number that on the left hand side that the exponent doesn't apply to, and I need to take care of that before I write it as a logarithm. So I'm going to divide both sides by 14 and get e to the 3x. 42 divided by 14 is 3. I'm going to introduce a logarithm. The e is going to be the base, and I'm going to switch the 3x and the 3, so I'm going to get the log base e of 3 equals 3x. Log base e is shorthand for ln, so log base e of 3 is the same as the ln of 3, so I'm going to write ln of 3. Now I need to solve for x. I'm going to divide both sides by 3, and for an answer, I'm going to get the natural log of 3 over 3. On this calculator, these 3's can't combine. You can't divide the 3's and make it a 1. To check this now, I would go ln of 3. My calculator needs the 3 to be in a parentheses, and it's not a bad idea to put it in a parentheses just in general. Had I did this for my answer, that's probably more mathematically appealing to look at, but it's not a big deal if I don't have it. For my decimal, I'm just going to do 0.36. Actually, this would round to 0.37. If on a test you wrote 0.37, fine. For my checking purposes, I'm going to use that. How do I check? I go to the original problem. Whatever I think the answer is, I change the x to it and make sure I get something close to 42. My keystrokes are to type the number 14. I don't need a times key, the times implied, but I need second and then ln to get the e, and then 3 times 0.3662. You can use less decimals. The more decimals you use, the more accurate your checking is. When I hit equals here, I get 41.999 blah 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 equals 42, so I know my answer is correct. Those were the only 2 problems where I needed that step of dividing before I introduced the logarithm. Each one of these problems needs logarithms because the answer is a decimal or because it's impossible to write the right-hand side with the same base as the left-hand side. So for 22, I can't write the right-hand side as 2 to some power. So I'm going to introduce my log. The 2 is going to be the base. I'm going to switch the x minus 4 and the 3, and we get the log base 2 of 3 equals x minus 4. I need to solve for x, so I'm going to add 4 to both sides. And the 4 can be written before or after the log. If I want to check, if you have log base, you would just go 4 plus log base 2 of 3, and I'll get 5.58 if you want 2 decimals, 496 if you want more decimals. On my antique, 4 plus log of 3 divided by log of 2. And you get the same 5.58496. So now for checking purposes, I need to go into the problem and see if that x is changed to 5.58496. Do I get something that's basically true? So let me see. If I go to exponent, this calculator doesn't show the exponent, so that exponent needs to be in a parentheses. And that should be close to 3. Because I carried a bunch of decimals, it's really close to 3. If I just carried 2 decimals, if I did 5.58, wouldn't be quite as close, but probably close enough for you to believe that your answer is correct. So this is the best answer. You don't need to give me any decimals. The reason you break out decimals is if you're wanting to check, because you're not going to check this answer. To put this in there, well, on this calculator I can do it. It wouldn't be that horrible, but on my old calculator it would just be just wretchedly awful. Last problem before we break into a part 2. So problem 24 is 2 to the x plus 5 equals 6. There's not a number multiplied by these exponential pieces, so I can go right into writing it as an exponent, or as a logarithm. The 2 is going to be the base. I'm going to switch the 6 and the x plus 5. And I need to isolate the x. I'll just minus 5 from both sides. You could write the minus 5 first, or you can write the minus 5 second. You don't need a decimal approximation for this. On this calculator, I'd have to go minus 5 plus log of 6 divided by log of 2 to get my negative 2.415037. On this calculator, negative 5 plus log base 2 of 6 to get that same number. If I want to check, I go to that exponent and see if 2 to the negative 2.415 plus 5 equals to 6. Easy enough to check, so I'll do it. See if 2 exponent negative 2.415 plus 5, close my parentheses. I should have had a parentheses around this, otherwise my calculator is going to be confused. So let me try to insert it in. That's no good. 2 exponent parentheses negative 2.415 plus 5. If your calculator shows it raises the exponent, you don't need the parentheses. If you have an old calculator like mine that's not raising the exponent needs to be in a parentheses. And I get 6.0000001 equals to 6. Good enough. That's close enough for me. I'm going to call that checked. So that's the first part of what I think is going to be 3 parts to this video. And a lot of these problems will make it on the test. Like always, peek at the practice test, because that's going to tell you what you really need to know from what we just did. All right, let me stop the video. We're at a half hour.